Hi, so my name is Simon Apers. I'm a chargé de recherche or CNRS researcher at IRIF here in Paris, and I think about quantum algorithms. So since the conception of quantum algorithms and quantum computing some 40 years ago, this has blown into a multi-billion-dollar business. And in fact, quantum computers might be available, like full-fledged big versions of them, in another 10 years. Now, strikingly, we don't quite know what we're going to do with them. My goal is to show that quantum computers will be useful for optimization. So in this picture is a jewel designed by a friend and physics enthusiast, Luisa Maria Ponceele, for the wedding of my partner and I. And it combines two things that are central themes in my research, which is quantum theory and graph theory. So on the one hand, this represents the notion of quantum entanglement, which is an invisible and paradoxical bond between two quantum particles. It can be miles apart. It's at the very core of quantum mechanics, and it's also at the core of why quantum computers can have a speed up and can give exponential, speed ups such as Shor's algorithm for factorizing large integers. On the other hand, it's inspired by what we call in graph theory the dumbbell graph, which is a graph that has two well-confined regions that are separated by a barrier or bottleneck. It's a toy model for the problems that you run into when doing optimization. And its study has led to the important notion of graph conductance or expansion, which in some precise sense measures that these bottlenecks are the only kind of obstructions that an algorithm for optimization has. So what brings together these two topics, and what brings me to this day, is this big question of, can we use quantum for optimization, and more specifically, can we use notions such as quantum entanglement to maybe tunnel through barriers like that. So quantum, there is this notion of quantum tunneling, which allows a quantum particle to go through high energy barriers, which exponentially suppress any classical dynamics for going through these barriers, right? Specifically barriers like this here. So it's a very exciting idea to try and use this quantum tunneling to tunnel through these optimization barriers. However, if one wants to prove something like that rigorously, you have to deal and put against one another the very fragile nature of quantum algorithms and quantum speedups versus the very powerful and legio classical algorithms that we have for optimization. So proving such a useful speedup and advantage of quantum computers for optimization is a challenging task, but it is bound to determine what we're going to do with quantum computers.